In this video tutorial, we will be looking at some trends or patterns of the periodic table. So let's begin with atomic radius. That essentially describes the average size of an atom. Now, the size of the atom increases as you go from top to bottom because the number of shells, or electron shells rather, increases as you go from top to bottom on the periodic table. Now, a common misconception students have is that they believe atoms get bigger and bigger as you go from left to right because it increases the number of protons, so obviously the atom must get bigger. That is incorrect. In actuality, increasing the number of protons actually makes it smaller and smaller. This is due to something called effective nuclear charge. The symbol we use is ZF. Let's compare these two electrons here. They are both in the second shell, and they're both attracted to the nucleus. However, they both have two electrons that block the view of the nucleus. So here we go, two electrons that block the view of the nucleus. This is known as electron shielding. So the electrons shield the nucleus, preventing it from attracting the electron as much as it could have without the electron shielding. And that of course affects the effective nuclear charge, meaning how well the nucleus can attract the electrons. Now what about these electrons over here? Do they not participate in electron shielding? Yes, they do, but they won't have as much of a shielding effect as electrons in the core shells. Obviously, this is a simplified diagram of the atom, so my explanation is not perfect, but you will notice that these electrons are on the same energy level as the electron that we're talking about over here. Because they're on the same level, it won't block the view of the nucleus as much as the core electrons. So again, comparing these two electrons, they are on the same shell, second shell. They have two electrons, primarily, that will block its view. So everything's identical, everything's fair between the two. The only difference is the number of protons in the nucleus of each atom. Since lithium has 3 protons, while fluorine has 9 protons, that means that fluorine is able to greatly attract the electron towards its nucleus more than lithium can. Due to the greater attraction, fluorine can hold the electron closer to its nucleus than lithium can. Thus, fluorine's atomic radius is slightly smaller than lithium's. And so the overall trend for atomic radius is to go in this direction, where the smallest atom on the periodic table is up in the top right-hand corner, and the largest atom on the periodic table is in the bottom left-hand corner. Now, if you wanted to compare between these two atoms over here, the one that has more shells is definitely going to be the larger one. But if they were side by side, the one furthest to the left would be the one that's larger because it has fewer protons to attract electrons. So the next trend we'll be looking at is called ionization energy. This is the amount of energy required to remove the outermost valence electron from an atom. Greater electron shielding decreases the amount of ionization energy needed to remove a valence electron. With greater electron shielding, it becomes more difficult for the nucleus to hold on to the electron. And so the further away the electron is, the easier it is to rip off the electron, the less energy required to rip off that electron, lower IE. Versus if you have very little electron shielding, the nucleus can now hold on to the electron very, very tightly, and then you're going to spend a lot more energy to try to rip that electron off, so you have an increased ionization energy. Thus, as the atomic radius increases, the ionization energy decreases. Now, first ionization energy is the energy required to remove the first valence electron, while second IE is energy required to remove the second valence electron, and so on and so forth. And so the more electrons you remove, the more difficult it is to remove subsequent electrons. So the third ionization energy is generally larger than the second, and this is generally larger than the first. Now let's take a look at these two scenarios. We'll talk about this in a little more detail later, but if you recall from grade 10, elements will want to lose or gain electrons in order to achieve a full valence shell, because a full valence shell provides stability. So if lithium loses this valence electron, that outer shell disappears, and now it has a full valence shell. In fact, it looks a lot like helium now, and we know that helium is very stable. It's a noble gas. So this lithium cation is pretty stable. Now let's go back to that neutral atom of lithium again. If it loses one electron, it'll become very stable because it will look like a noble gas, helium. So the ionization energy required to rip off this electron is going to be pretty low because it's not going to take a lot of convincing for lithium to want to become stable. So there you go, the first ionization energy, a very low amount of energy required to rip off that first electron because it wants to become stable. It doesn't take a lot of convincing to do so. But now that lithium is stable, removing another electron would destabilize the lithium cation and make it unstable. But if you really want to remove that second electron, it's going to cost you a lot of energy. And so the second ionization energy for lithium is going to skyrocket in comparison to the first ionization energy. Alright, so removing the first electron didn't take much convincing because now lithium is stable, but to remove the second one would make it very unstable, so it's going to cost you. Now let's take a look at beryllium. Removing one electron will cost you a certain amount of energy. That would be your first IE. But now beryllium is only one electron away from being stable like helium. So again, it won't take much convincing to remove that second electron from beryllium. So the jump from the first ionization energy to the second ionization energy won't be that big of a gap. Now with this stable beryllium cation, trying to remove a third electron, that's going to cost quite a bit of energy because again, you're making it less stable. So just like in this example, there's going to be a huge jump in ionization energy from the second to the third because removing that third electron really destabilizes it. Alrighty. Now before we move ahead, I need to do a quick little detour. Bowling ball in the air, bowling ball on the ground. Which of these two bowling balls has more energy? Which of these two bowling balls has more potential to do damage? Well, obviously the one in the air has high potential energy, while the one that's sitting on the ground has low potential energy. But tell me, which of these two bowling balls is more stable? Well, the one that's sitting on the ground is going to be more stable than the one that's floating in the air. So, in general, if you have high potential energy, you tend to have low stability, and vice versa, if you have low potential energy, you tend to have high or greater stability. Now, how can this bowling ball become more stable? It needs to fall down to a more stable state. But that would mean it has to have low energy. But how does it go from high energy to low energy? Well, according to the law of conservation of energy, you can't destroy energy, you can't create energy, but you can convert it into a different form. So as this bowling ball drops to a lower and lower potential energy state, it's bleeding off energy in the form of kinetic energy, or the energy of motion. Alright, so in order to become stable, I have to lose energy. Well, the opposite is true. In order to become unstable, I have to give it energy. In this case, I'm giving it kinetic energy, the energy of motion, to lift the bowling ball up into an unstable state. The next trend we'll be looking at is called Electron Affinity EA. Electron affinity is the change in energy when an electron is added to an atom. So while ionization energy is the change in energy when you remove an electron, EA is the change in energy when you add the electron instead. Now take a look at lithium. With lithium, you can either gain 7 electrons to achieve a full valence shell and become stable, or you could lose 1 electron so you could have a full valence shell. Obviously, it is much easier for metals to lose 1 valence electron than it is to gain 7. With a non-metal like fluorine, however, it is much easier to gain 1 electron than to lose 7 electrons to achieve the full valence shell. So by adding 1 electron to fluorine, you have made it very stable. And if you recall, high energy typically means low stability, while low energy typically means high stability. And of course, energy can't be created or destroyed. So when we add this electron to fluorine, we make it very stable. In the process, it goes from a high energy state to a low energy state, or we say it's ground state. But of course, energy cannot be created or destroyed, and so the energy lost, or released rather, in this process is known as electron affinity. It gets a negative value because we're releasing the energy. So the energy is being lost by the atom and given off to the surrounding area, and that's why EA is a negative value. Looking at lithium, however, gaining an electron doesn't really help the lithium become super stable. Remember, it would have to gain 7 more electrons to achieve a full valence shell. So adding 1 extra electron doesn't really help lithium all that much. That is why its EA value is much smaller than fluorine's. By adding electron to lithium doesn't really do too much in terms of stability, so very little EA is released, but adding electron to fluorine does a lot for its stability, so a lot of energy is released. But what if you try to add an electron to something that's already stable? Helium, for instance. So helium is already quite stable. By adding an electron in, you destabilize it. as we saw over here, if you have low stability, you have high energy. So in the process, you're giving energy to the helium to make it unstable, and that's why its EA value is going to be positive. And so typically, noble gases, their EA values will be a positive value because adding an electron to it makes it unstable and in the process adds energy to the atom. Now, it's much easier to add an electron to a smaller atom than it is trying to add an electron to a larger atom. Larger atoms, the nucleus is so far away with so much electron shielding, it's hard for that electron to get locked in. Whereas with a smaller atom, because the nucleus is so close to where the electron is, it's much easier for the electron to be attracted to its nucleus. As such, electron affinity generally increases from left to right and bottom to top, all right, where the smallest atoms are the ones with the highest EA, and the largest atoms are the ones with the lowest EA values, which is the same pattern for ionization energy as well. Now, the last trend we want to look at is called electronegativity, EN. This is the relative measure of an atom's ability to attract shared electrons in a chemical bond. So how well can an atom attract electrons towards its nucleus? This is a scale from 0 to 4, where 0 has low attraction and 4 means high attraction. Just like the last two trends, the smaller the atom, the greater the attraction for electrons, while the bigger the atom, the farther away and the less the attraction for electrons. As such, greater electron shielding decreases an atom's EN value, while an atomic radius increase results in electronegativity decrease. Alright, so what I'd like you to do now is to try out this practice worksheet. Take a look at the first question. Which of these three letters, D, E, or J, has the largest atomic number? So D, E, and J are located here. D, E, and J. So which of these three elements has the largest atomic number? Obviously the answer is J, and you can find the answer at the bottom over here. Alright, so try them out, and if you have any questions, let me know. In our next video, we will take a look at the different types of chemical bonds and how to draw line diagrams.